Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is my pleasure to have Maziar Gudarzi with us today. Maziar received his PhD degree in 2005 from the Sharif University in Iran, and since 2006 he has been a guest associate professor at the Kyushu University in Japan. And today he will talk to us about his work on software and architecture techniques for cache leakage reduction in nanometer-scale embedded systems.
Thank you. Thank you. Good morning. Thank you very much. Yes, today it's a great pleasure being here with you in this flagship research institute of Microsoft in this very beautiful place. My talk today is regarding power consumption and reducing power consumption, some techniques for power reduction. Well, if you ask a hardware design engineer or a hardware specialist regarding techniques to reduce power, he or she can tell you lots of different kinds of techniques, tens or hundreds, and each of them would be perhaps useful for or customized to one part of the system. But what we particularly are interested in are software techniques for doing this, and the smart things that you can do with your software so that total power consumption would be reduced. Just imagine, would it not be very interesting or excellent if you could connect your MP3 player to your computer and just upload a new version of software to that, and after that it would play, while it would have played 10 hours of music for you, now it plays 20 hours. Would it not be great? Or you could do the same with your mobile phone. This is actually what we strive to achieve, doing some smart things in software so that without big changes in your hardware, you could achieve some power reductions. Let me first start by the framework in which we work. This is a national project, CREST, under the scheme CREST in Japan. It is composed of 4 big parts, and we are one of those parts, and our part is we are in Kyushu University. Nagoya University is the other university involved, and Toshiba is for evaluation. The main target in this project is reducing total power consumption of processor-based embedded systems by 2 orders of magnitude. The project is going to run for 5 years, and it has started in 2006. One big view behind this is that we target embedded systems. Embedded systems, you know, these are anything like mobile phones, MP3 players. And there are big reasons why we are targeting embedded systems. If you take a look at the history, well, personal computers started in perhaps 1980, 1981. And in 2008, it is estimated that total number of personal computers would get to 1 billion. And it is also anticipated that by 2015, it would get to 2 billion. So it took around 27, 28 years for the first billion, and around 7 years for the next billion. But the first mobile phone was introduced in 1991 in Finland. And in 2006, there were 2.5 billion subscribers to mobile service. You see that for the first billion of mobile systems, it took around 12 years, and for the second billion, it took only 30 months. And in 2008, at the beginning of 2008, 4.3 billion cellular phones have been manufactured. And only in 2007, 1 billion has been manufactured. You see that the number is going very high, very quickly reaching very high numbers. So that's one reason behind our targeting and the project targeting embedded system. But it does not mean that the techniques that we provide do not work for high-performance computers. power is also, although power is very important in embedded systems because you have a battery and you want to use it as long as possible, but in high performance computing it's also very important. Even at the moment, 1.5% of total electricity produced in the United States is used in data centers. And in 5 years, it's expected to reach 4.5%. So reducing this total power consumption or reducing the amount of electricity bill that you pay would be a very important goal. Well, let me first give some very basic background on power consumption. I don't know whether you are familiar with that or not, but just a few points would be very helpful. Well, the dominant technology for implementing chips today is CMOS. CMOS is basically things like that. As you see, in each case, only one transistor is on. Each transistor can be viewed as a simple switch. You can turn it on or turn it off. For example, here, this one is on because you have a 1 here, and this other one is off. There are three main mechanisms for power consumption in CMOS technology. The first one is dynamic power. This has traditionally been the main source of power consumption, and it is all about capacitors. When you have a wire, you have some capacitor. And when you want to assert a 1 here, you have to give some electricity, some electrical charge inside this capacitance, the capacitance that would be here down to here, so that the value would be 1 at that point. And then when you want to make it 0, then you have to discharge the capacitor. And this is power consumption. This is called dynamic power consumption. The basic way to reduce this kind of power is to reduce the capacitor or the number of switching that you do on that. The second way is short circuit power. When you want to switch this system, for example, from 1 to 0, in very short amount of time, both transistors would be conducting. In normal mode, you see that only one of them is on, the other one is off. So there is no current actually between these two. But for a very short amount of time, there would be some high current between these two. But in today's technologies, this is negligible. And the third one is a static power or leakage. This is the big point. This is becoming the main source of power consumption in today's systems. Actually, what in the ideal case, you expect this transistor to be completely off, to conduct nothing, but it does not hold anymore in today's technologies with technology scaling. There is a small current going through this transistor in today's technologies, and it is going to be more. I will show you in a few seconds the result of such a change. So you do not really like this. The basic mechanism to get rid of this leakage is to turn off the circuit, meaning that you just do not let supply voltage be here. But you can only do this when the system is not working, is not doing anything useful. And especially for some things like cache memory, you cannot do that because you have some values or some important values there. So you need to do some other stuff for that. The other thing is for reducing the leakage power is that you have some knobs there. I will talk about them, VTH and TOX. These are two knobs that very effectively control the amount of leakage that you have in this transistor. But the disadvantage is that they cause reduction of performance of your system. So you have to be careful about that. When thinking about technology scaling, when we go to lower technologies from, say, 90 nanometer, we go to 65 nanometer, dynamic energy is reduced. Since you are doing the smaller things, the capacitance is reduced, and also since everything is tinier, you have to reduce the power supply. And as you see here, there is a quadratic relation between dynamic energy and supply voltage, and also capacitance is here, so dynamic energy is effectively reduced. But the bad thing is that there is this relation between delay and VDD. When you reduce VDD, as I said, in order to keep the delay as before, you have to also reduce VTH. VTH is threshold voltage. This is one of those knobs that I said. This can very effectively control the leakage. It has an exponential relationship, as you see here. So static energy has an exponential relation to VTH. So you reduce it, the static energy is increased very highly. The other knob is TOX, gate oxide thickness. Again, you can reduce this, and you have to do this because you are scaling the technology. So in order to keep your transistor working, you have to reduce the oxide thickness when you also make the transistor smaller. So as you see, static energy is increasing. The final result is that for a given application, say here MPEG-2 process application, when going from from 118 nanometer technology down to 45 nanometer, the total amount of the share of leakage in total energy consumption of system is increasing very highly. As you see here in 180, there is almost no leakage. In 90 nanometer, it would be something like this, 30% or something, and it would quickly go to 50% and higher. Actually, this is a pessimistic in terms of off-chip memory. The bar here you see here is off-chip memory power consumption. Yeah.
A little confused with your graph. Is there active power here as well for when the chip's executing? Because I notice there's off-chip memory and cache and leakage energy. What about?
Yes. They are also all in this bar. Processor and off-chip memory, all of them. The green bar is only for data for cache, and the lower one is for leakage. And the point is that I said the share of leakage would be even higher than this because we have assumed that this part is the same for all technology nodes. And that's not really true. It would be reduced.
So is the leakage power of the caches alone, or this is leakage power for the entire chip?
This is leakage power of cache. For other parts of the chip, yes, you still have leakage, but the main, as I will show you in a few seconds, the main consumer is cache. So here it is only cache. And you can do much, you can turn off some parts of processor so that you reduce leakage.
What's the intuition behind why the cache is looking so much more than the processor?
The main reason, I will talk about it just in a few seconds, right? Before getting to that, I have another bad news, and that's the leakage is also exponentially dependent on temperature. So you have a higher temperature, you go to higher temperature, you have higher leakage. And when going to smaller technology nodes, since the amount of leakage is increasing, so you also see a higher increase in total leakage. Yeah.
I can't remember what Kelvin maps to in terms of Fahrenheit. Can you
Well, this is Kelvin, so
Yes,
this is
I
100
thought
degrees.
273 plus Celsius. Oh, yeah.
Yes, this is 100 degrees. Sorry about that. I should have written it. Well, this is taken from. Okay, so this is 100 degrees.
Okay.
Centigrade, not Fahrenheit. Fine.
Okay.
All right. Okay, so you see static power would be even increasing with temperature. The other bad news is leakage variation. These results, you can see lots of similar results from Intel, IBM. There is a big difference in the same, for different chips in the same frequency in terms of leakage. In other words, maybe the MP3 player that you get, maybe the one that you get works for 20 hours, and the one that I get may work only for 5 hours, because the leakage is very high.
The chips are on the left here.
Yes.
Why don't they throw the fews that are on the right away?
Because of cost. You need to sell anything you can. Otherwise, Intel would not do.
But the The scenario that you just depicted is not fully accurate, right? In the sense that if we are both getting to MP3 players, then these parts would be typically binned based on their frequency and leakage characteristics, and there would be a very narrow window of uncertainty around the target frequency and power consumption of the particular part that I get. And if you're getting a part that's lower power for higher, for the same frequency, then you might pay more, but there wouldn't be that uncertainty.
Well, the point perhaps goes at the end to what you said about the cost. Well, yes, they do frequency binning. For example, they bin some of the chips around here in the normalized frequency. These are not working as fast as the other ones around here, so they would be much cheaper. But how about these ones? All of these chips around here have the same frequency. So ideally, you would like to sell them at the same price, but you cannot do that perhaps because of the change that you see in terms of battery lifetime. So again, they need to perhaps do some binning around here, or get rid of some of these, but it means that the loss of money.
Well, the second thing that you could do is to, after post-manufacturing, you could apply body biasing, and therefore you would reduce this variation. So everything would translate into the y-axis and the square axis.
There are many things like that, but adaptive body biasing, but all of them have difficulties associated with them. Well, adaptive body biasing is very expensive to implement because you need a special manufacturing process. And
I'm just saying body biasing, not necessarily the adaptive version.
Well, you have to be adaptive in that case because different chips need different biases.
Sure, across chips.
Yeah. Any question?
Do you have an accurate information about like how many percent of the chips are over 10x in this case, for example? Because this graph is not that informative at all. Like 7x is a shocking number, but in that cloud, if there are 1 million points, and if there are like on the order of 30 points, then it should be just negligible.
I don't have accurate results. As you see, this is taken from DAG 2003, but Sani Nassif in ASP DAG 2008 showed a similar thing again. He's from IBM, I think, or maybe, I apologize if I'm making a mistake. But the point is that it's not negligible. If it were negligible, they would certainly neglect it. Okay. The other point is, this is what I said. I will talk about cache and why leakage is so important in that. As you see in most processors, whether it would be a high-performance processor such as Alpha or embedded processor such as PowerPC or StrongR, a large part of the chip consists of cache. You see 40%, 75%, over 50%. And as I said, you have valuable information in the cache, so you cannot turn it off. Simply turn it off, you would lose the data, and then it would result in high performance degradation. And the other point is that most parts of cache are often idle. You have lots of data there, you cannot ignore them, but most of the time you are not accessing them. This is the problem. And one other problem, I will get to it in a few slides, is variation. Since most of the chip is consumed by cache transistors, you have to design the transistor with the smallest size. And the smaller the size, the higher the variation. I will show this in a few slides. The higher variation means that, again, leakage is changing very much among different parts of the cache. So that's why we have focused on cache memories and while talking about leakage reductions. So today, if I find time, I will talk about four techniques, four of our more recent works. The first two ones are compiler techniques, actually pure software techniques. The third one is an architecture one, and the last one is a combination of software and architecture.
Briefly talk about your assertion that the caches are idle most of the time. Even if the processors are very active, that's the case. Your L1L2 caches just aren't being used.
Oh yes, yes, indeed. Even it is. Although cache is still taking care of the mostly used data, but it's still only a small percentage of that data is used at any time. So most of data is not used.
At any instance in time.
The point is busy, but particular lines in the cache.
Yes, indeed. Just a tiny fraction of the cache most of the time.
So you said a slide ago that you couldn't simply turn off the cache
Yeah.
because you had data in it, but there has been, for example, proposals for cache decay,
Absolutely.
in which you basically make the observation that there's this generational behavior in cache access.
That's correct.
If a cache line has not been touched for a while, you invalidate it and then turn it off.
That's right.
So
But you have some performance degradation, but well, they have taken care of that and have shown that performance degradation is not very high.
right.
But the main problem is implementation. So far as I know, there are no or very few real implementation of that, although cache decay has been proposed in 2002. Right. That's the main problem. Okay. So the first technique is some variation-aware compiler techniques. The basic point is that I will show you that due to variation within die or intra-die variation, the amount of leakage in a SRAM cell depends on the value that you store there. So if you take care of the value storing in each SRAM cell, you can reduce total leakage. This is the basic mechanism. As I said, when going to lower technology nodes, the transistors are no longer perfect. The parameters of the transistor would change. These changes can be viewed over different chips on the same wafer. This is called die-to-die variation, and it can also be seen even within the same die. So this is called intra-die variation. Both of these variations have become very important, especially from 90 nanometer forward. You see lots of intra-die variation. And the final result is that even adjacent transistors with the same design size have different parameter values. The parameter that I am talking about is VTH. Remember that knob that I talked about regarding leakage? So two transistors with the same size, and even if they are adjacent to each other, have different VTH values. This mainly comes from a phenomenon called random dopant fluctuations. For the sake of time, let me just say that, in previous technology nodes, you would have a big channel area, a big transistor, and lots of atoms, thousands of atoms would go there. These atoms are dopant atoms that they basically control the features of the transistor. But when you go to smaller sizes, you have just tens or hundreds of these atoms. So the statistical variation of these numbers and the way that they would be, whether they are uniform or non-uniform, completely defines the features of that transistor. That's why you see random variations. And as I said, here you see that the variation is huge in a small transistor. And in cache, remember that you have very small transistor because it is area constraint. So you see the worst case of variation in cache. Some empirical results. This one comes from 113 nanometer. Shows 13% variation in current, in leakage current, while 67 millivolt variation for VTH inside the same chip. And you see again the exponential variation, exponential relation between VTH and subthreshold leakage. So the final result is that exponentially, the leakage of two transistors would be exponentially different. And in terms of a single SRAM cell, the final result will be shown here. This is a single SRAM cell. This is actually two cross-coupled NOT gates. This is one NOT. This is the other one. And these are two transistors for accessing this SRAM cell. This is a standard 6-transistor SRAM cell. If it is storing a 1 here, the other node would be 0, and these 3 transistors shown here would contribute to leakage in this case. But if you change the value, the other transistors would be contributing to leakage. And as I said, the leakage of these transistors is different. So the final result is that leakage when storing 0 is different from the leakage when storing 1. This is the basic point that we take advantage of in our techniques. In order to find out how much difference would result from this fact, we ran some Monte Carlo simulations. The value of intra-die VTH variation, the values are taken from ITRS roadmap. ITRS is International Technology Roadmap for Semiconductors. This is actually the organization that works as the reference for the future estimations. So in 2007, it's expected to have 33%. You see, it is going very quickly to 112% variation in 2018. Well, actually, this shall not happen because such a variation cannot be really tolerated. But anyway, these show the trend. And we measured the total difference between full match of the values to the preference of the SRAM cells and full mismatch. And the final result is the maximum leakage saving, as you see here. So in 2012, with 58% variation in VTH, you could expect something around 60% difference between full match and full mismatch.
Maybe I'm misunderstanding, but it sounds like you need an oracle that tells you for every memory cell whether it's cheaper to store 0 or 1 there. Is that right?
You need to test it. You need to do some testing. You need to store 1 in each SRAM cell, then store a 0 there. In both cases, you need to measure the current, which is flowing to the chip. So you find out whether that SRAM cell is.
But if you look at an aggregate of, let's say, the entire memory, or even one 4K block of memory or something, it seems like the leakage would be about the same because these variations are going to be randomly distributed across all the individual cells. Is that right?
Well, if you do not take care of the values, it would be almost the same. But if you, sorry.
But the point is, how do you measure it? Can you measure the difference between?
Yes, indeed.
When you flip one bit,
Yep,
so you work your way through memory, flipping one
Point.
bit.
In the paper, we have shown the reference to some Japanese manufacturers that measure 0.1 femtoampere. Femtoampere is, if I'm not making a mistake, 10 to the minus 15th power. So 0.1 femtoampere is very, very accurate. But, well, you do not need to be that accurate. What you want to measure is to measure hundreds of nanoamperes because the leakage is high. The leakage in a 90-nanometer technology that we have, the leakage of a single transistor is around 1 nanoampere. So if you can measure around 100 nanoampere, that's fine. Because you do not want to be just as accurate as 1 nanoampere. You want to differentiate in the cells that have the highest difference between storing a 0 and a 1. So if there is a, say, 100x difference between storing 0 and 1, that cell would be a good target for doing value control.
How long does it take to measure power of a bit?
It depends on how you measure it. If you measure it using external equipment, it would be, I know some references to testers that do it in 100 kilohertz. So 100,000 samples can be taken in 1 second with the accuracy of 100 nanoampere. But what you want to do is, the best way to do that is to use things called BICs, built-in current sensors. You design some small circuit inside that can measure the current for you, and that's the way to do it.
And it would be faster than 100 kilohertz that way?
Certainly, and much more accurate, because you are doing it inside the chip. If you go outside the chip, you have.
What is the rate you get?
Yeah.
With that approach?
With chip in, if built-in, I think. Well, it still depends on the accuracy that you want to get, but you can go to.
Do what
For this, you can get over 1 megahertz. Easily go over 1 megahertz.
Are you suggesting that this testing, this feasible, will be done at design time once this information?
No. For every chip, you have to do it.
Right. So what I said is post-manufacturing before you ship the part.
Yes. If you do the built-in current sensor, you had better do it, measure it in field. So that, for example, when you buy your mobile phone, you run a setup or something like that, the software goes and measures these values and stores them somewhere to take care of that. This is the best way to do it.
Leakage power is also going to depend on environmental conditions, and you're not necessarily going, in fact, they will change in the field also.
Yes, but the main point is that the relation between leak 1 and leak 0, meaning is still the same. Well, yes, temperature goes high, so leak 1 and leak 0 both go high, but if leak 1 is higher than leak 0, it remains to be higher than leak 0.
Is static for a particular transistor? It does not change over time. It doesn't get worse.
Yes, it does. Over time, it gets worse.
Over what time period? So if you do the test at the beginning and then a day later, all my leakages change.
Not a day, but over years it does. Over years.
So use cell phones for more than a week.
Sorry.
When you get your plan, right?
Yes, actually, aging is becoming the other problem. It is one of the problems that reliability people are working on.
Briefly, to pop up a level of the power savings you're going to get here compared to the base power of a phone with a screen and all the other pieces that are on it. I mean, what percentage power savings do you think this type of work will have an impact on something?
Well, well, of course, if you think about a complete embedded system such as a mobile phone, the main part is LCD panel. And the wireless, yes, certainly. But the point is that once, as long as you do not impact them, it's good to save power anywhere.
So what's the percentage of your power budget, would you say, on a phone that comes from leakage?
You mean compared to the total power? Well, I do not have the complete value, precise. Sorry?
Do you have an order of magnitude, just a sense of where it was?
I don't have accurate results, but I think the power consumption of LCD would be at least 5 times than processor. But we are mainly concerned in processor. In the project that I said, CREST project in Japan, 3 other groups. One of them works on wireless, the other works on optoelectronics, I think, and another one on LCD. Okay, so finally we get that some cells prefer 0, meaning that the leakage would be less when storing 0. Some other prefer 1. So what we want to do is to give every cell the things that it prefers. In data cache, maybe it's very hard to do because you have basically random values. But for instruction cache, you can do lots of things. At least we did these 3. The first one is reordering instruction within each basic block. Given a basic block, we reorder instructions inside that so that the matching would be improved. And we also change register-operands of instructions so that, again, the matching between the instruction and the corresponding cache cell would be improved. And the third technique says that let's initialize the cache. So since some parts of the cache are not used by the application that you are running, we suggest to initialize those parts to the best value, to the best match for that cache. Sorry?
Is it not possible to just
Well,
turn-
if you could, you would certainly do that, but it's very expensive to do. That's what I said in regarding cache decay. Yes, if it is possible, it's better to turn them off. Well, for the sake of time, let me skip these parts. We can talk about them. Well, this is one point. This is important since we need to take care of each chip differently. Each chip has its own leakage profile. So you need to optimize for each chip differently. So the way to do that is the way that we propose to do that is to get the application binary in PROM for the first time then get real-time operating system, do the optimization for you, change the application binary, and restore it in the PROM, and finally in the subsequent executions, it would be run without needing optimization again. In other words, you can get your mobile phone, you can run some optimizer on that, and after that, the system works fine. Kind of installation process, say. Again, these are simple points. One important point is only that since we are working on basic blocks, we do not change the address of basic block, we do not change the size of basic blocks, so the hit and miss ratio of instruction cache is the same as before. Just some changes in data cache may happen, but in our experiments it was less than 1% change. This is important since you can do instruction reordering in a bigger visibility, but it would impact instruction cache. And this is the register renaming technique. We just changed the register operands. These are the instructions of M32R. This is an embedded processor. I guess nobody has ever heard of M32R. No, this is Japanese. This is very popular in Japan. These are the operands that you can handle. So some of the instructions can be changed. And this is some results from running one application. Say here FFT application. This is on a two-way cache. This is 8 kilobyte cache. And the results show that the vertical axis shows the number of cache refill operations. So in these parts, you have 0 cache refills, meaning that part of cache is never used. So you can initialize all of them. This is the algorithm. Let me again skip it. It's simply a list scheduling algorithm. We ran the algorithm of benchmarks from MyBench benchmark suite. These are the characteristics of the benchmarks. And to take care of the variation, we use Monte Carlo simulation of 1,000 chips. And these are the final results. For each application, you see 2 bars here. The left-hand side bar is divided into 2 parts. This is the original total leakage. Some parts are consumed. Some leakage corresponds to the used parts of the cache. The yellow one is unused parts, and the right-hand bar for each application shows the improved one.
Could you show us some of the parameters of the system that you modeled?
Oh, this is it is M32R processor. Cache size is 8 kilobyte, direct map cache, 1,000 caches, and these are the average results. For each cache, as I said, each chip is different from the other one in terms of leakage profile. So you have to do it over 1,000 and then average. So any specific points of?
I meant the microarchitectural parameters of the processor itself.
Well, the processor is M32R. It is fixed. It is a RISC processor, 5-stage pipeline processor. It is single issue and running on 200 megahertz. Okay, so yeah, here as you see, in case of, for example, JPEG, the number of unused cache cells is very low, so you do not get as much as leakage reduction as you get on FIR. FIR is a very small benchmark, so you get lots of power saving here using cache initialization. Here you get you see the average saving results for techniques 1 and 2. This technique 1 was instruction rescheduling, 2 is register renaming. Overall, they give us around 20% reduction alone on the used parts of the cache, and technique 3 gives almost 55% reduction for the unused parts of the cache. So the total is here, and the maximum saving, the chip, meaning the chip that gives you the maximum saving, is shown here. There is just a few percentage of more saving here.
Variations you had come from real mappings of chips that told you the variations of the leakages, or did you, how did you come up with those?
We just simulated using Monte Carlo simulation. The basic point, the basic parameter is VTH variation, the amount of VTH variation, which is usually expressed in terms of percentage of 3 sigma over mu. So when you say 10%, means that 3 sigma is 10% of the mean value. We get this value, we generate different VTH values. We have the basic leakage of an ideal transistor, so we get the leakage of each transistor in each case.
Just for all the different...
Sorry?
Forget it.
So you're looking at improving the leakage in the instruction cache, but of course there's the heap and the data, the data of the application. Did you do anything to try to optimize the leakage in that area?
In the heap itself, if it is implemented, well, we are working on cache. So we did not work on off-chip memory.
But the L2 cache. The data cache, I'm talking about.
Oh, you're talking about data cache. I said data cache, the value that we have in data cache is basically random. So we have not done that. But yes, if you find some proposal to take better advantage of take better control over the value stored in the data cache, yes, it would be fine. But we did not do that.
You've made it sound like these are very practical techniques that you could actually implement with hardware that we have today. Why? But there must be something hard about it that you haven't, that I can't see because you did it in simulation instead of doing it in real hardware. So what's hard about it? Why can't it be done today?
Well, we did simulation because we did not have enough budget to implement a real chip on that. But for practical implementation, I think we need to spend some time on the design of the current sensor. This is the main point.
So the current sensors that you would need, that it's research that we don't have access to.
Well, there are lots of solutions for that because there is a special kind of testing called IDDQ, and this is just measuring currents. So we can reuse them, but they are usually designed for higher currents, although they can be customized for very small currents that we want. So that's the basic point.
So going back to this possible comparison to cache decay. So for cache decay, people have reported, if I remember correctly, 4x reduction in cache leakage power for minimal performance loss. And what you're saying is true, that there's an area penalty to learning certain counters, etc. But this technique is not free either because you need these current sensors that you need to put on chips. So how would the overhead compare between the two quantitatively?
Well, one point is that in cache decay, you do not just need some counters, some extra counters. The basic point is that you need to be able to control each cache line separately. So you need to have some controlled supply voltage line for each cache line. This is the main problem, I think, not the counters. The counters would not be a big point, and that's why I think it's not been implemented. But here you just need some current sensor for the entire cache. So it is basically very small, the current sensor, especially if you design it inside the chip.
In mobile phones, are the caches direct mapped or are they associated?
It completely depends, but direct maps are sometimes preferred because of power efficiency. In set associative caches, you have much higher power consumption, but they are more effective in terms of performance. So sometimes, processors such as ARM, they sometimes even have 32 cache ways. But basically, people prefer direct map caches in embedded systems.
So another thing you could do is you could try compressing the code so it takes up less from the cache. Have you looked at the effect of that on power?
I'm sorry, I didn't completely
You
get.
could compress the code so it takes up less space in the cache.
Mm-hmm.
There's a lot of redundancy in
Right.
instruction streams.
Right.
So have you looked at that in terms of how much the cache you would need, how much power that would require for these benchmarks?
Well, compressing is one basic technique for reducing the cache size required, but it needs dynamic power. You need to spend some dynamic power for compressing and then decompressing when needed. Well, with technology scaling, since I said that dynamic energy consumption is reducing, that may be one basic point for going toward that. But we did not compare our work to that one. Okay. So the breakdown of leakage savings achievable here is, well, around 10% can be achieved with the technique 1, another 10% with technique 2, and the rest comes from cache initialization. Effect of cache size was studied. As you increase the size of cache, as you decrease the size of cache, the amount of unused parts of cache would be reduced. So in the case of MPEG-2, for example, coming from 16 kilobyte to 4 kilobyte, you see that all the cache lines are used, so the unused part is reduced. But for small cache, for a small application such as FIR, this does not happen very much. The same holds for cache associativity. At higher associativities, again, you get better usage of the available cache capacity. So in case of MPEG coming from direct map to 8-way cache, again, the number of unused cache becomes 0. So you get basically only techniques 1 and 2 to reduce leakage. But for FIR, again, you see that not much difference happens. On the effectiveness of techniques 1 and 2, since in direct map cache you have one-to-one relationship between each instruction and the cache memory, the technique can be much more accurate. But in set associative caches, you have, for n-way cache, you have n different ways.
Looking at this seems very unrealistic. I mean, you're basically looking at the computational kernel of an application. So on my handheld device with a screen, I'm not going to want to run an MPEG decoder and not run the code that actually displays the image on my screen. So I'm not going to be able to go and initialize all the unused cache locations outside of the MPEG-2 decoder to some random value that minimizes cache size, because I'm going to have code in those locations that are going to be my system code, my display code, or whatever the UI code is there as well. So, is this actually going to work in a real system as opposed to benchmarking a kernel?
In embedded systems, there are lots of systems that you have only one application to run. In that case,
but my point is that an application is more than a computational kernel. Right. I mean, there's no point in running an MPEG-2 decoder if you don't do something with the output of it.
Well, any application that you have, well, you may say that, well, MPEG-2 is just a kernel application, but for any other application you can run, and if you find no unused cache, okay, you can still use techniques 1 and 2, and they give you around 20% reduction in leakage. That's why we have analyzed the effect of different cache sizes, different associativity. Yes, it reduces the amount of leakage saving if you do not have enough unused cache lines, but if you do have, okay, let's reduce cache in that case. Okay, so techniques 1 and 2 the techniques 1 and 2 have to know which cache line has the highest probability of hosting the instruction. Since we do provide this information to the optimizer, then the result is that no matter what is the number of cache ways available, the performance of these two techniques is almost the same.
Pretty non-intuitive to me. I mean, it really seems like with 8-way associativity, because you're effectively 8. You don't know where it's going to go. You have a 1 in 8 chance. So why doesn't it dramatically drop off with associativity-wise? But what's the intuition?
Well, in these simulations, it turned out that only one of the cache ways have the highest probability of hosting that cache line, that instruction. But yes, in general, it may not completely hold. In these applications, in these simulations, this did happen. We ran the simulation, the entire application, and using instruction set simulator, and this gave us the cache way with the highest probability. The longer, yes,
you're saying the renaming and whatnot took into account the way in which it expected the cache to be, the cache line, where it expected the cache line to go?
yes, that's the information that comes from instruction set simulation of the benchmark. Okay. So regarding the third technique for cache initialization, again, you have to pay some dynamic energy to execute some instructions to initialize the cache so that you get some leakage saving. So there should be some break-even points between these two. And we measured it using the typical energy consumption of instructions in M32R in our implementation. Our typical implementation was on 0.18 micron. So these values are actually worst case break-even points, because if you're talking about 90 nanometer, then the power consumption of M32R processor should also come from 90 nanometer, but these results are from 0.18. But as you see, basically in most applications, it is a fraction of a second. But in the worst case, for JPEG, it is around 3 seconds, meaning that if your application is going to, or if your embedded system is going to run for 3 seconds or more, in this case, it is okay to do cache initialization. Otherwise, it would not give you some leakage saving. This also goes back to the question over there that if you do not have enough unused cache lines, then cache initialization would not be a good choice. Okay, with technology scaling, the amount of variation, as I said, is going to go very high, over 100%. We analyzed this effect with different sigma VTH, and as you see again, with technology scaling, the amount of saving would increase. This is intuition. Sorry?
Do you have to do the cache initialization at every context switch?
What we assumed here was only no. We assumed that once it is done at boot time of the processor. We assume that this processor is going to run only that application.
Right, so in a system that's running more than one, you're going to have to rerun the initialization.
Yes, in that case, you had better, not necessarily at any context switch. I think that the best way is to explore. I think many ways can be done. You can do it every context switch. You can do every time that you change the application, not necessarily at pre-specified time slices.
I guess this is a question that I had already asked a little while ago, but I'll maybe ask again. I'm having trouble putting this in context, and that I feel like we're sort of 5 layers deep, and if you were to break down energy use of a device, the device has a screen and a big wireless transmitter and a bunch of chips on it. And then one of those chips has both a processor and a cache, and then within that cache, there's some that leaks and some that's dynamic. And, within the leakage, you can reduce that by 30%. And if you pop all the way back out to the top level, I don't have an intuition if you're going to get 5% or 0.0005% total power reduction for the device as a whole.
Well, as I said, I do not have accurate results to give you how much would be the total power consumption in the embedded system, because it completely depends on what embedded systems you have, what is the number of stacks that you're talking about, and what are the specific. Sorry?
I guess I was hoping you had intuition for maybe one typical case, not an exhaustive, since of course it's going to be very application sensitive and device sensitive, but I guess I just didn't have a sense for if it would ever matter, or if it matters within a certain set of applications, or for devices that have certain usage scenarios, or...
If I have an embedded device that uses 1 watt base power,
What?
Do you have any sense of the budgets? You seem to have a sense of the budgets of all the different devices that make up an embedded device. So we're hoping that then you could give us some sense of how the savings is going to impact the overall base power device.
Well, for the processor, the M32R processor that we had in 0.18 consumes 200 milliwatts at 50 megahertz, right? But why I said that I do not have accurate results is because I do not have the accurate results of the power consumption of LCD or wireless parts. That's why.
People are asking for order of magnitude, not.
Order of magnitude estimates.
Order of magnitude, I think.
Are we going to save 1%? 1/10%?
I think it would be very well. This say if you get 50% here, it would be reduced to perhaps around 10% or 5% in the entire system because of the total power consumption of other parts. But the point is that in embedded system, you do not really talk about the entire. Well, for big picture, that's fine. But as long as you do not impact the other parts, it is fine to reduce some part. You usually focus on one part of the system. You try to optimize that part. Yes, it is certainly important to find out which part is the best target.
It's possible that by focusing on that part, you have an unintended impact on the other parts, which causes base power consumption overall to go up. That's where, I'm sorry, go ahead.
Maybe screens
Yes.
and phones are the future. Just as voice recognition and just that would help.
It simplifies stuff.
Yes, certainly you should be very sensitive to, very accurate to what kind of optimization you propose. You should show that in embedded system computing, it is very, the people in the conferences, I mean, are very sensitive to what kind of impact you may have on other parts.
So if there's this much variation, one of the possibilities is that the transistors fail entirely.
Mm-hmm.
So have you thought at all about using a similar technique? I mean, basically the fact that if you have these failed transistors, using an analysis like this to actually avoid, using them at all, or using them in a way that would make them not work.
That's one actually concern for SRAM designers. Yes, they are very concerned on whether with these variations the final SRAM cell is going to work or not. And as you see here, these are the forecast of ITRS. They said that we would have over 100% variation in VTH, but this is certainly not a thing that is going to happen, because if you have such a thing, then that SRAM cell would not really work. But to have just some forecast or the trend on how much leakage you can get, we just use these values. Yes, reliability is very important. And some people even say that the SRAM cells especially may not be shrunk anymore. But it is still to be seen. Okay, so algorithm execution time on the processor is just a few seconds. And finally, the summary of this part. Well, I have not even come to the other parts. Anyway, this was a simple software technique. And one important point, I think, beauty of the technique is that you do not, we address the parts of the cache that are actively being used. This is important because usually, as I said, the basic technique for leakage reduction is to disable that parts that are not being used. But how about the parts that are being used? Techniques 1 and 2 that we propose can address those parts. This can be applied to scratch pad memory, and also you can have some more sophisticated optimizations for value control on the cache. Okay, this is the second technique. Let me go very much faster if I want to have the 4. All right. This is the static register renaming again, but this time for asymmetric SRAMs, asymmetric cell caches. These are some results from some other researchers showing that the 0, 1 contents of cache are biased towards 0. So if you design the SRAM cell such that the leakage when storing a 0 is much lower, then you can save more energy. This is the basic mechanism that they do for that. As I said, here for storing a 0, only these 3 transistors would contribute to leakage. So if you control the knob and increase VTH, you can save energy. They proposed 4 designs, and these are the normalized leakages, the first and second column. This is the normal cache, and this is designs 1, 2, up to 4. These are the 4 designs, the best 4 designs of them. And we basically do register renaming again, and basically you get application source, compile it, you run the static register renaming and store the result in instruction memory. If your instruction cache is designed with asymmetric SRAM cells, you get some leakage saving. This is the experiment setup. We avoided binary manipulation in order to have the simulations done much faster. So again, these are the benchmarks that we used. And for different designs, you see different leakage savings. For the best design, where leakage in case of 0 is 1 and leakage for 1 is 14, you get around 30% reduction. And for the other 2 with 40 to 50 and 14 to 43, you get around these values. But in this case, where leakage 0 and leakage 1 are almost the same, the leakage saving is not very high.
Is that the saving for that design with the optimization turned on and turned off?
Yes.
That's what you're comparing?
Yeah.
Are there differences in power usage between the designs?
Between the leakage of the register operand bits in the cache for 2 cases. One with the regular case, this is the base cache, the other with the optimized cache design. Sorry, the base cache is not a regular one. The base cache is design 1, for example, in this case, without optimization, then compared to the same design but with optimization.
When I see this 30%, should I think that that's really good and I want design 1? Or is it possible that design 4 is actually much better because the power usage in design 4 is lower?
Here it is clear, I think, because leakage 0 and leakage 1 are much lower than this. So in terms of leakage saving, it is higher than this, and also in terms of absolute leakage, it is much lower than this. But in these 2 cases, you are right, the absolute value should also be taken care of, because leakage 0 and leakage 1 are almost the same in this case. So although the saving is also the same, the comparison of these 2 would be a little bit more sophisticated. I have results, but in a different slide. So
We've got leakage 0 equals 1 and leakage 1 equals 1. In other words, just design something with very low leakage, even if it has no opportunity for optimization.
Sorry, I didn't.
Is there a design 5 that you could make where leak 0 equals 1, leak 1 equals 1?
I don't think so, because if you could do that, you would certainly do that to reduce total leakage.
On the previous slide, he had what this impacts in terms of delay to move both of these to vary them separately. So presumably would have some kind of trade-off in that regime.
Yeah, maybe it helps here. You have some trade-off. Yes, you reduce leakage 0 and leakage 1 here, but you also have delta delay. So the speed of the SRAM cell is also getting impacted or changed, at least here. Yes, you give 5% delay, and these 2 are also some parameter of reliability of the system. So there is a trade-off. But basically, it's not possible to design it another SRAM cell to have both leak 0 and leak 1 to be 1. Okay, for different cache sizes and cache associativity, the result is the same. And this second technique is simpler to finish. This is a software technique, as you see, up to 33% leakage saving. The other technique, I think this takes too much time if we want to finish. So let me skip this. Let me just give you the basic mechanism. The point here is that you have delay variation. So different SRAM cells in the design have different delays. What we want to do is to again use that knob. We change VTH so that the leakage would be exponentially reduced. But this results in a shift in the delay of the entire system. So some of these SRAM cells now would be outside the target delay of us, right? How do we take care of them? We propose to have additional cache lines, additional cache ways. In other words, you have at the beginning, you have, let me show this slide. At the beginning, you have a 4-way cache here. Then you increase VTH from, say, 270 to 320. And some of the cache lines now become delay violating. How do you take care of them? You add an additional cache way here. But since the increasing VTH results in exponential reduction of leakage, the linear increase of number of SRAM cells in terms of additional cache way would still benefit in the final system. In terms of showing that in a figure, it can be viewed like this. This is the SRAM delay distribution. We turn the knob, so delay distribution moves like this. So some additional SRAM cell delay violating SRAM cells happen here. And we take care of this number, assuming that this leakage distribution, this delay distribution follows Gaussian distribution. We have some analytic formula so that the number of these delay violating SRAM cells and cache lines would remain such that the total cache capacity remains the same. So this is the basic mechanism that we use to get some leakage saving. Depending on the amount of delay variation, which has been shown to be around 3% in 90 nanometer technology, you can get some leakage saving as shown here. With one additional cache way, you can get these values, and the second one, the green one, shows for 2 additional cache ways. But if you have 5% delay variation, you can get more leakage saving even in case of 2 additional cache ways. And the results finally on instruction cache would be like this. On compressed benchmark, with one additional cache way, you can get around 22%, but the second extra cache way does not help you as much as before. So leakage saving is almost the same as this case. So the 25% additional area would not be worse. For unified cache, for L2 unified cache, it would even better serve you, because in L2 cache, the amount of leakage is higher. The share of leakage to dynamic power is much higher in this case. But in data cache, it does not help you as much as before. The main reason is that in instruction cache, you have the sequentiality point. The basic power consumption mechanism in set associative caches is due to tag comparisons. So in a four-way cache, you have to do 4 comparisons per access. But in instruction cache, you do not really need to do that, because most of the time, the next instruction is in the same cache line that you accessed before. So in that case, you can skip tag comparisons. If you do that, you get the results that I showed you here. But in data cache, you cannot do this. For every cache access, you have to compare all the 4 or 5 cache tags. And yep.
Are you taking into account the fact that adding an extra way means you have less cache, and so your performance is going to be reduced by the fact that you have less cache?
We do not have less cache. We have the same cache size or even more, because you see here, we do it such that just as before, for every cache
Right, no,
set.
I mean because you had to reserve space on the die for these extra lock.
Okay. If you want to keep the area the same as before, no, it would not help. But we assume that we pay the extra area. In other words, the cost of doing this thing is the additional area that you have to have in the die.
How does that compare to spending that extra area to give you more cache and thus make your benchmarks run faster?
Yes, but how about power? The power would be also increased because you have larger cache. You also and you have the same VTH as before. But in this case, we have larger cache, but we have changed the knob. We have turned the knob so that the leakage is reduced.
Yeah, I don't know. I mean, you have more power, but you might run faster, so you might have less. I don't know. I'm just wondering what.
Well, you run faster, but the leakage is 25. In this case, for example, if you have four-way cache, the leakage would be also 25% more in that case, because you have 25% more SRAM cells, right?
So the total energy consumption may nevertheless decrease in this case.
The total area.
No, so you're going to run faster, but you're going to leak more.
Mm-hmm.
So if you complete
The total energy consumption, you mean? Main. Mm-hmm.
Battery.
That's right. Okay, so this technique gives you these savings. And okay, let me get to the final one. Temperature aware configurable cache. The basic point behind this is that leakage depends on temperature. So if you can configure your cache depending on the actual temperature of the chip, you can save lots of energy. I've shown already that dynamic energy is reducing with technology and static energy is increasing, and also dependence of leakage to temperature. So for here in case of quicksort with reduction in cache size, you get a much higher number of cycles for executing the cache, for executing the application. So dynamic energy is increased with reduction of cache size, but for the same reduction of cache size, the leakage energy is reduced because you have a smaller cache. So the total result would be that for different temperatures, you have different optimum points. So you had better optimize the cache for the given temperature in which the system is working. In other words, just to give some view, it means that if you get your mobile phone to inside a car parked in hot environment, in sunshine, in a summer, the mobile phone may not work as long as it would do in a cold winter because of leakage. So this is the basic change that we want to have in the cache architecture. We want to have only configuration controller here, so that the configuration of the cache can be controlled under control of software, and software takes care of reading out the temperature at runtime and configure the cache, and finally it gives you something around depending on the temperature that you use and whether you work on instruction cache or data cache. Some savings, as you see here. Well, time is really up, so if you are interested, please come and let's talk about it more. So at the end, I would say that the basic message that we want to do, we want to transfer, is that what we have done and we intend to continue is that we take care of the technology trend in very low levels in electrical engineering and the electronics down there, and we try to find out some effects that can be utilized at software level and system level so that total power consumption can be controlled. In future, the three ways that we want to, we intend at the moment at least to do more investigation is on real-time operating systems. This is the first one because RTOS is becoming much more popular in almost all embedded systems. It is already quite popular in mobile phones. Chip multiprocessors and multiprocessor system on chips are also becoming much popular. And this is one other area of future work, and reconfigurable system on chips. And I had some slide that it's not in this one. The amount of money that you have to pay today for manufacturing a chip is becoming multi-millions. So designing one chip per application is no longer cost effective. So you have to design a chip that can be used in several different applications. And one of the ways to do that is reconfigurable system on chips. When you have some processor inside the chip and some FPGA blocks around that, there are lots of such products already available from Xilinx, Altera, and other FPGA products. This is the other final point that we are going to extend our research to. I have some other presentation on other works in Kyushu University and also my PhD work at Sharif University, but if anybody would be interested, I would be very happy to talk and discuss it more. Thank you very much, and any questions anymore?